In this section of the course, we are going to focus on a new topic, sequence data. Although deep learning initially became popular for being really great at working with images, it was not long until deep learning also proved its dominance with sequences as well. Some examples of that are text, speech, and even financial data such as stock returns. In this lecture, we are going to discuss why we should model sequences and also look at some examples. So let's start with the simplest kind of sequence data. At least this is what most people think of when they think of a sequence. That is a time series signal. A time series signal can be any continuous valued measurement taken periodically. For example, a company's stock price is probably the go-to example. Another famous example is the airline passengers dataset. This is actually more practical than you might imagine. If you can forecast the number of passengers you will have on your airline, you can do all sorts of things, such as making sure the airport has enough workers to handle all the passengers. You can modify your prices to reflect demand. In fact, that's what people do. Uber's surge pricing is an example of that. It could also help airlines decide where to put their resources and marketing. Actually, forecasting airline passengers is a surprisingly big deal. There are all sorts of articles and papers written on this topic. I just found out that China will soon surpass the United States as the world's largest aviation market. Another example of time series is weather tracking. This is something we all probably make use of on a daily basis. You don't want to go outside without your umbrella if it's going to rain. One interesting fact about weather is that it's a dynamical system. That probably sounds complicated, but some terms you probably have heard of are chaos theory and the butterfly effect. This is that even if we have the exact deterministic equations to describe a weather system, our forecast will still become more and more incorrect the further into the future we try to predict. That's pretty counterintuitive because you would think if you have the exact equation for something, then you should be able to calculate all the future values precisely. But due to the butterfly effect, this is not actually true. As the saying goes, a butterfly flapping its wings in Tokyo can cause a tornado in America. Small imprecisions like numerical roundoff error in your computer will ultimately lead to your weather forecast being completely wrong eventually. This is actually really relevant to us because when you think of time series and RNNs, you automatically think, how can I use a powerful model like an RNN to do time series forecasting? Another great example is speech or audio, for which the obvious application would be speech recognition. Now, I'm not sure how many of you are into audio engineering or music production, but if you are, then you should definitely recognize this as a time series. Just open up your favorite audio file in the open source program Audacity, and you'll see how it's just a time series of sound amplitudes. So all in all, time series are everywhere. Another type of sequential data is text, which of course deep learning also excels at. The interesting thing about text data is that it can be treated as a sequence, but in machine learning, you don't have to. In the olden days of machine learning, we couldn't deal with sequences very well, and so we resorted to more naive models. The typical way of doing this would be to create what is called a bag of words feature vector. Basically, it works like this. Suppose you're doing document classification. So for example, you take an email and you want to know, is it spam or not spam? So what do? Well, first, let's take a big long feature vector with length equal to the number of words in the English language. Then, for each word that each component of the feature vector represents, we insert the count of how many times that word appeared in our email. So suppose, for simplicity's sake, there are only 5 words in the English language: insurance, loan, pickles, backpack, and football. So now, let's say our email contained the word insurance 3 times, the word loan 1 time, and the rest of the words 0 times. then our feature vector would be 31000. In this way, we can convert every email in our dataset into a feature vector. And then we get back to the situation where we can say all data is the same. As our input X, we again have a table of numbers. They just happen to represent word counts. For the labels, it's just 0 and 1 for spam and not spam. As usual, you can run any binary classifier on this, such as logistic regression or a neural network. But there's a problem with these bag of words representations. When we only use word counts, we lose information about the order of the words. Here's a simple example of why it matters. Consider the phrase dog toy. Now consider the phrase toy dog. Clearly, these two phrases mean something completely different, and yet a bag of words model would treat them the same. If you want to learn about how to deal with text, that will be a major topic of the next section, but this section will focus mostly on modeling continuous valued sequences of data. Usually, when we think of a sequence, we think of something like what you see here. This is just like how we started with linear regression. The simplest way to look at it is a line of best fit. This is the most basic thing we can do because we can see it. So analogously, for sequences, we're going to think of one-dimensional sequences because we can see them. And while this is technically a sequence, we can extend this concept a little bit. Recall that when we were working with non-sequential data, like what you saw with linear regression, that in general, the data was of shape n by d. N is the number of samples and d is the number of features as usual. Even when we are doing one-dimensional linear regression, we still use a two-dimensional array to represent the input data x. We still say it's n by d, it's just that d is 1. So for time series or sequential data, let's think about what the shape of the data should be. First, consider just a basic sequence like a stock. How can we represent the length of the sequence? Should it be n? Should it be d? In fact, it's not really either of these. We don't want to consider each point in the sequence to be a sample, nor do we want each point in the sequence to be considered a feature. As a side note, we could do that, but that's not general enough for RNNs. So it's clear we need a new letter to represent the length of a sequence. How about the letter big T? That seems pretty intuitive because the word time starts with the letter T. So it makes sense if we're dealing with time series or any other continuous valued signal that the length of the signal should be denoted with a new letter, T. Considering what you just learned, I'm going to tell you that the shape of our data, when we're dealing with RNNs, will have the shape n by t by d. Let's break down what this means. We know that n is the number of samples and d is the number of features. And you just learned that t is the number of steps in a sequence. As you can see, this is a three-dimensional signal. N is the first dimension, t is the second dimension, and d is the third dimension. When you're dealing with sequence data, sometimes students can get confused about which thing is n, which thing is t, and which thing is d. So I think the best way to understand this is by example. Let's suppose we want to model the path that people take to get to work. So you can record data from the GPS in everyone's car. In this scenario, what is n, what is t, and what is d? Well, since we're modeling people's trips to work, one sample will consist of one person's single trip to work. You might record some data over multiple days, in which case that person could have multiple trips to work. That would count as multiple samples. Alright, so what's D? In this case, D is probably 2 because the GPS will give you both latitude and longitude measurements. Okay, so what's T? T is the number of lat-long measurements taken from the time the person embarks on their journey to work until they arrive at work. So let's say it takes a person 30 minutes to get to work, and you record lat-long coordinates every second. In that case, the number of steps you would have is 30 times 60, which is 1800. So the length of your sequence T would be 1800. Now you might be wondering, doesn't it take each person a different amount of time to get to work? And indeed, you would be correct. In TensorFlow and Keras, we generally work with equal length sequences, so just assume that this is the case for now. We'll discuss this in more detail later. For now, let's think of more examples. Here's an example of where d equals 1, so it's kind of like the simple case, analogous to our one-dimensional linear regression. A simple scenario for this would be stock prices. A stock price is a one-dimensional signal. The vertical axis is price, and the horizontal axis is time. In other words, to have a signal where d is bigger than 1, we would have more measurements per unit time. For a single stock price, we just have 1, the price. So what would n be in this case? This is a complicated question actually, but let's consider again something simple. Let's say we want to break up our stock price signal into windows of length 10. So our task might be something like, using 10 sequential measurements of the stock price, try to predict the next stock price. In this case, n would just be the total number of windows of length 10 that we have. By the way, this should remind you of some of the convolutional arithmetic we did. If your total sequence of stock prices has, say, length 100, and you want to know how many windows of length 10 can be taken from this sequence, that's just 100 minus 10 plus 1, which is 91. In other words, if you have L consecutive measurements, and you have a window of length t, then the number of windows is L minus t plus 1. Of course, with stock prices, you might not want to measure just one stock. There could be multiple stocks. So here's an example with stock prices where d is bigger than 1. Imagine, for example, that you've taken measurements for 500 stocks, just like the S&P 500. Now you have the stock price for 500 different stocks over time. That means d equals 500. You can again artificially make a window of length t, and then the number of samples you have is just the number of these windows. Here's another example which is somewhat futuristic. Imagine you are working with Elon Musk at Neuralink and you record voltages from electrodes placed in the brain. In this scenario, d is equal to the number of electrodes. At each point in time, you're going to have measured d different voltages at different locations in the brain. One of the early applications of brain-computer interfaces was moving a mouse cursor on a screen and typing. In other words, everything you need to use a computer. So suppose we are trying to predict the letter or number you are thinking of or want to type, and this is based on the voltages recorded from your brain for 1 second as you think of that letter or number. Now let's say measurements are taken from the electrodes at a sampling rate of 1 sample per millisecond. That's 1,000 samples per second. That means for 1 second, in the time we make the recording of you thinking of the letter, we've collected 1,000 measurements at each electrode. So t equals 1,000. N, as usual, would be the number of letters that you thought of. So if we did a test where you had to think of a series of letters and collected 10,000 1-second recordings, that means n equals 10,000. One question you might be pondering is, why is our data of shape n by t by d? Why not n by d by t or some other order? And in fact, there's no particular reason it needs to be this way, except for the fact that all Python libraries for machine learning conform to this standard. This is just like our tabular x data where we have n by d, or our image data where we have n by h by w by c. This could just as easily be d by n, or n by c by h by w. In fact, we've already seen that in PyTorch and Theano, the convention is n by c by h by w. So this stuff is not set in stone. My goal in this course is to show you how we do things in PyTorch. In Python, the general pattern is that we always put n first, so that should go without saying. There are certainly other libraries which by convention do not put n first. The other convention is that we put the number of features last. So that's why we have n by d, where d is the number of features. This also makes sense for images, where we have n by h by w by c, because c is the number of feature maps, which is the analogous version of features for image data. And this also makes sense for sequence data, because this d still represents the number of features. By the way, one important thing to do is visualize the shapes of the data in your mind. Before, where we had n by d inputs, we visualized that as a rectangle. Rectangles are two-dimensional, so that makes sense. Now we have a three-dimensional object, so it is no longer a rectangle, it's a box. So when you hear me say n by t by d, you should automatically think of a box without needing me to tell you to do so. This should be very helpful as you write your code and reason about how RNNs work. As promised, one thing we have to consider is, what if we have variable length sequences? It's clear that this is a pretty common scenario. Just think of sentences. Not all sentences have the same number of words. Some sentences have 1 or 2 words, and other sentences have 100 words. This is actually a very interesting question. In the past, I've written code that can handle sequences of variable length. The problem is, this gets complicated fast. Another problem with this is that it means you'll be using inefficient data structures. If you have an n by t by d box where t is constant, then we can store this in a single numpy array. That is efficient because a numpy was written to be efficient. But if t is variable and depends on which sample we are looking at, we might use the notation t of n instead, since t depends on the sample n. In this case, we cannot store this in a single numpy array. Instead, we would have to use a list, which is inefficient.
On the other hand, there are some inefficiencies with constant length sequences as well. In PyTorch, it's easiest to start with constant length sequences, so that's what we'll be doing in this course. This is the case with other modern deep learning libraries as well, such as TensorFlow and Keras. If we do end up having variable length sequences as input, what we can do is pad each sequence with zeros, so that they all have the same length as the longest sequence. For example, if your longest sequence has 100 words, then even sentences with 1 or 2 words would be the first 1 or 2 words and then 98 or 99 null values. As you can imagine, this is going to take up a lot of unnecessary space and processing time because the neural network still thinks your entire n by t by d box is full of legitimate data. Simultaneously, it does make coding RNNs much easier, so it's a trade-off. Ultimately, this is the way we do things in PyTorch. So unless you wanted to write your own custom code, this will be our data format for sequences.
Luckily, what PyTorch does is a kind of compromise between constant length sequences and variable length sequences. The idea is, instead of having all your sequences padded to be the same length as the longest sequence, just do that across single batches. As you know, our method of training in deep learning is batch gradient descent, so we're only going to look at a subset of our training data at any given step. During that step, we can pad the sequences in the batch on the fly so that they are only as long as the longest sequence in that batch instead of the entire training set. Now you might think this is still going to be a problem if you have one sequence in your batch that has length 100 and all the rest are length 1. Then you'll have 99 padded values in all those shorter sequences. But what PyTorch does is, for certain generators, it tries to group together sequences with similar sequence length. So the batches you see will still be random, but not as random as they would be if you didn't care about the sequence length. Of course, if you're creating your own data generator, you would have to write that kind of custom code yourself. Finally, note that it's possible to take things one step further and actually deal with variable length sequences, almost without dealing with padding. This part of the lecture is optional and outside the scope of this course, so don't feel like you have to understand this to progress through this section. The idea with this is that, Although your batch will be of size n by t by d, where t is the length of the longest sequence in the batch, if we know the length of each sequence in the batch, then we can be intelligent about which data we process. Ultimately, it looks kind of weird because your batch of data will still be a padded tensor. But then, using the lengths of each sequence, you'll convert it into an unpadded tensor. Then, you'll pass it through the RNN unit and get back an unpadded output. And finally, you still have to reapply the padding and then pass your data through the rest of the neural network. Unfortunately, doing this requires you to keep track of the lengths of each of your data sequences, even while shuffling and iterating over randomized batches. This approach is more involved, so at this time, it's going to be considered to be outside the scope of this course. Alright, so what are the main takeaways from this lecture? Number 1, when you have sequence data, that means your data isn't just a single feature vector, but a value or set of values that can vary with time. Number 2, lots of people think of time series, which are one-dimensional values that vary with time, but we can also have d-dimensional vectors that vary with time. Some examples of that are weather readings from multiple weather towers, or brain signals from multiple electrodes on the brain. Number 3, in modern deep learning libraries, you're limited to constant length sequences. If you want to do better, you can use constant length sequences per batch instead of the whole dataset. If you want to do even better, you can convert those constant length batches back into variable length sequences, but that's outside the scope of this course. Number 4, by convention, we'll organize our sequence data to be of shape n by t by d, where n is the number of samples, t is the sequence length, and d is the observation dimensionality. You should always be visualizing these shapes in your mind, which will help your understanding immensely, but I won't prompt you to do so, and therefore you'll just have to remember to do it yourself.